All right, so how many questions? There will be maybe around 12 to 14 questions on midterm. All right, so first problem. Many investigators have suspected that workers in the tire industry have an unusual incidence of cancer. Suppose the expected number of deaths from bladder cancer for all workers in a tire plant in January 1st, 1964 over the next 20 years based on US mortality rates is 1.8. If the Poisson distribution is assumed to hold and 6 reported deaths are caused by bladder cancer among the tire workers, how unusual is this event? So we have a rate of 1.8 deaths per 20 years. Right. And 6 reported deaths are caused by bladder cancer among the, how unusual is this event? So let's find probability of X being greater or equal than 6 deaths, where X follows Poisson distribution. So for Poisson distribution, for Poisson random variable, we have a single parameter, which is rate, lambda, which also shows expected number of occurrences of that event in given time interval. So in our case, it's equal to 1.8. Let's stop here for a second. Let me ask you the following question. Let's assume that number of events, let's say number of accidents per year is given as 4 events per year. So 4 accidents per year. Now, if I were to calculate number of accidents per 2 years, what should be my rate when using Poisson random variable? So let's assume that I want to calculate it, the number of occurrences, the number of accidents per 2 years. What should I put here for my rate in Poisson random variable?
So that's mu t, right? So that should be 8.
Yep, absolutely right. Okay, now we're clear on that. Now let's find how unusual is this event of getting 6 deaths. So this is 1 minus probability X is less or equal than 5. Let's calculate that first using Google spreadsheets. Share my screen. All right. Okay, guys, can you see my screen?
Yes, we can.
All right, so I need to find probability that X is greater or equal than 6. This is 1 minus probability that X is less or equal than 5. So for Poisson distribution, we use this Poisson function. X is number of occurrences, which is 5. Mean is given as 1.8, right, guys? 1.8. And we'll put for cumulative truth, since we need CDF of our random variable. So the answer is 0.01. Okay, and we see that this event is extremely unusual. Okay.
I'm sorry.
Yes. Mm-hmm.
the probability that x is less or equal than 5, but not 1 minus this one.
Could you repeat that?
I mean, don't we need to subtract 0.01 from 1?
We are not subtracting 0.01 from 1. We subtracted.
Oh, it was in the equation of the Google spreadsheet.
Yeah, so 1 minus.
Sorry.
Yeah, okay. All right, now. Suppose a similar analysis is done for stomach cancer. In this plant, 4 deaths are caused by stomach cancer, whereas 2.5 are expected based on US mortality rates. So lambda is equal to 2.5, and here we have X number of occurrences equal to 4. So we need to find probability that X is greater or equal than 4, which is 1 minus probability X is less or equal than 3. Okay, now let's get back to our spreadsheet. So this is 1 minus Poisson. So these two functions are the same. 2.5. We need what do we need? Probability X is less or equal than 3, right? And rate is 2.5 for cumulative output true. Okay, so it looks like this event isn't so unusual. So this is 24%, approximately 24%. So that event isn't that unusual, right? All right, guys, now let me show you how to do the same commands using R. All right, guys, can you see my screen?
Yeah.
All right, so we need to calculate. So let's come back to our case. In first case, we need to calculate 1 minus probability X is less or equal than 5 when rate is 1.8. So let me write this down for you. We need 1 minus probability X is less or equal than 5. So this function here is a CDF of our Poisson random variable, right? So I need 1 minus CDF of Poisson random variable. In R, to find CDF, we always start by typing down P. So for any random variable of interest, we start our notation for CDF from P, and then we need Poisson distribution, and then here's my P Poisson, then will give me CDF of my random variable. So Q here is 5, lambda is, what was lambda, 1 second, 1.8. Okay, so I need to calculate 1 minus that. So 1 minus P plus 5, lambda is 1.8. Okay, so here we calculated probability that X is greater or equal than 6 using R, and the answer is the same, right, guys? Okay, now let's calculate our second probability. 1 minus probability X is less or equal than 3. So 1 minus, again, for CDF, we start from P. So less or equal than 3, and rate was 2.5. Okay, so same probability, 24%. All right, then P stands for distribution, so stands for CDF. If you want to find, for instance, if you want to generate, let's say, a list of random numbers from that random variable, from that distribution, let's say we want to generate 10 random trials from, let's say, binomial distribution. So we start with R. So for any distribution, we start from R. That will generate us a list of random numbers from specified distribution. So let's say from binomial, let's generate a list of 10 random numbers. Let's say size is 100 and probability, let's say 0.5. So basically, here we generated 10 sample cases from our binomial distribution where n is equal to 100 and probability of success is 0.5. So basically, we have 100 coin tosses of a fair coin. So here are the answers. Then if we want to find PMF of that random variable or density, that stands for D. Then let's say binomial random variable. So let's find probability that X is equal to 51 out of, let's say, 100 coin tosses. And let's assume that coin is fair. Then probability of that is 7.8%. Okay. And let's say if we want to find probability that X is less or equal than 51, then we use P. 51, size 100, probability 0.5. If you leave out all other, if you do not include your other parameters, they will set to default values. Okay. All right, now let's come back. All right, so should we use RStudio? Yes, you can use R or you can use Google Spreadsheets. Both will be fine. I would recommend that you learn at least commands for spreadsheets, since using calculator to calculate this will consume a lot of time for you guys. Okay, now next problem. Assume the number of episodes per year of otitis media, a common disease of the middle ear in early childhood, follows Poisson distribution with parameter equal to 1.6 episodes per year. Find the probability of getting 3 or more episodes of it in the first 2 years of life. So we need to find probability that X is greater or equal than 3. In first case here, our X follows Poisson with parameter lambda is equal to 1.6 multiplied by 2, so 3.2. Okay, now let's calculate that. So this is 1 minus Poisson. X was greater or equal than 3, right? So we need 2. Mean is 3.2 and motive, we put true for that. All right, so 6.62%. Now find the probability of not getting any episodes of otitis media in the first year of life. So we need to find probability that X is equal to 0. So here we don't need CDF. In 1 second, let me get back to the question. The first year of life. So now we are working with with 1 year period. So X follows, in second case, X follows Poisson distribution with parameter of 1.6. Okay, so then we need to find Poisson dist. 0, mean is 1.6, and we'll put false for cumulative. We don't need CF, we need PMF. So this is 20%. All right. Any questions so far, guys? All right, next question. An interesting question in pediatrics is whether the tendency of children to have many episodes of otitis media is inherited in family. What is the probability that 2 siblings will both have 3 or more episodes of otitis media in the first year of life? So let's start by calculating probability that one of the kids will have otitis media. So let's find probability X is greater or equal than 3. First 2 years of life, so lambda is equal to 3.2. So this is equal to 1 minus Poisson. 2 rate is 3.2 and cumulative is true. All right. 62%. Now we need to find probability that 2 siblings will both have 3 or more episodes of otitis media. So we can model now that with binomial random variable. So let's call that random variable y. It will count the number of occurrences of otitis media 3 or more times for 2 children. So y will follow binomial distribution with n is equal to 2 and probability of success equal to this value that we calculated here. I believe it was 0.62. So this is 0.62. Okay. Now we need to find probability that y is equal. So 2 siblings will both have 3 more. So probability y is equal to 2. You can also just square is at 0.62, but to generalize our problem, let's calculate that using binomial distribution. Right, so this is my probability of success. Then I need to calculate for binomial distribution is the function is binom dist. Number of successes is 2, number of trials is 2, probability of success is 0.62. And for cumulative, we'll put false. We need PMF, so 0.38, so 38%. So this is 0.38. All right, next. What's the probability that exactly 1 sibling will have 3 or more episodes in the first 2 years of life? So here now we need probability that y is equal to 1. Let's come back. Copy this down. So probability of success. Okay. We need to find number of successes is 1. Okay, and this is selected correctly, false, right? So 0.47, so 47% for random variable being equal to 1, so 0.47. What is the expected number of siblings in 2 sibling family who will have 3 or more episodes in the first year? Okay, number of siblings. Okay, so we need to find expected value of random variable y. Who remembers what was the formula for expected value of binomial random variable? with parameters n and p. So let's assume that you are, yep.
NCK and then P to the power of N and Q to the
No,
power of.
I mean, not distribution function, not PMF of binomial. Expected value of.
NP.
Yes, absolutely right. So NP. So let's assume that, let's give let's give a simple example. Let's assume that you are throwing a coin 100 times. Let's assume that probability of success, let's assume that this is a biased coin and probability of landing on heads is equal to 60%. And you are throwing coin 100 times. What is the expected number of heads you should expect? So 100 multiplied by P, right? So 60, you should expect on average that you'll get 60 heads. By the way, guys, I believe in that spreadsheet, in that worksheet. Let me check. Yeah, we will show how to derive expected value for binomial random variable in a second. Okay. All right. So for expected value of binomial random variable is NP. In my case, N is equal to 2 and probability of success is 0.62. Okay. So 1.24 is the number of occurrences, is the number of kids that I should expect will have 3 or more cases of otitis media in the first 2 years of life in a 2-sibling family. All right. Okay, guys, any questions? If no questions, let's keep moving. An experiment is designed to test the potency of drug on 20 rats. Previous animal studies have shown that 10 milligram dose of the drug is lethal 5% of the time, the first 4 hours. Of the animals alive at 4 hours, 10% will die in the next 4 hours. Okay, let's. What is the probability that 3 or more rats will die in the first 4 hours? Okay. Let's start. Let's just solve this problem right away. So what's the probability that 3 or more rats will die in the first 4 hours? What is the probability of dying in the first 4 hours? This is 5%, right? Then we are looking for binomial random variable X follows binomial distribution. Number of rats N is equal to 20. Probability of success in the first 4 hours is 0.05. Okay, then we need to find probabilities that 3 or more will die in the first 4 hours. So this is 1 minus probability X is less or equal than 2. Okay. So 1 minus the induced number of successes is 2, number of trials is 20, probability of success 0.05, cumulative true. Okay, so this is 8%. All right, guys. Next problem. What is the probability that 2 or fewer rats, suppose that 2 rats die in the first 4 hours, what is the probability that 2 or fewer rats will die in the next 4 hours? So 2 rats have died in the first 4 hours. It means that after first 4 hours, we have 18 rats left. What's the probability that 2 or fewer rats will die in the next 4 hours? So now this time, X is binomial random variable. N is equal to 18. So 18 rats left after the first 4 hours. And in the next 4 hours, the lethality rate increases to 10%. So P is equal to 0.1 now. What's the probability? 2 or fewer. Okay, so we need to find probability X is less or equal than 2. Okay. 2 number of trials 18, probability of success 0.1, cumulative true. All right, so 73%. 73%. What is the probability that 0 rats will die in the 8-hour period? 0 rats will die in the 8-hour period. Again, we are going to model this with binomial random variable. Now this time number of successes will be n is equal to 20, but we need to find P, probability of success, where probability of success will denote probability that a rat dies in 8-hour period. So die in 8-hour period, let's denote it as from 0 to 8. Okay. Let's draw our sample space to illustrate what's happening, guys. We haven't been working with sample spaces for a bit. So here's my sample space. So first 4 hours, 5% of rats will survive, will die in the first 4 hours. So let's denote this region as so this blue region here is for rats that die in the first 4 hours. Okay. Other 95% are going to 95% are going to survive our 4-hour period. So that black box is for the rats that survive first 4 hours. Okay, now out of of the animals alive at 4 hours, 10% will die in the next 4 hours. So this region here in red, it represents the rats that survive first 4 hours. Then out of this, 10% are going to die in the next 4 hours. So let's note this in green here. Out of these who survive, 10% are then going to die in the next 4 hours. So let's give it a name. Die in 4 to 8. And then the left part here, let's color it in purple, will be the rats that survive the 0 to 8 period. Okay. All right. Now we need to calculate probability of dying in this interval here, which we can denote as so either one of the two events will happen. Rat can die in first time interval, first 4 hours, or it can die in the second interval from 4 to 8 hours. Okay, guys, what can you tell me about these two events? Dying in first interval and second interval.
They're mutually exclusive.
Yep, absolutely right. So they cannot happen both at the same time, right? So what does that mean? How do I calculate their union then?
Just summation of
Yep,
rules probabilities.
absolutely right. Absolutely right. Thanks. So probability of dying in first 4 hours plus probability of dying in 4 to 8 hours. Now I can find probability of dying in first 4 hours directly. I believe we already we have that information. So this is 0.05, right? 5%. Now we can express probability of dying in the next 4 hours as probability of as the following conditional probability as dying in the next 4 hour period, given that that rat survive first first interval 4 hours multiplied by probability of surviving first time interval. Okay, so here we use total probability rule. Then what is probability of dying in 4 to 8 given that you survived first time interval? So this is exactly the definition of this probability here, right? Of the animals alive at 4 hours, 10% will die in the next 4 hours. So this is equal to 10%. So 0.05 plus 10% multiplied by probability of surviving in first 4 hours is 95%, 0.95. Okay. So then that will be my probability of success, and number of trials will be 20. Now I need to find 0 rats will die in 8 hour period. Let's get back to spreadsheets now. So 0.05 plus 0.1 multiplied 0.95. Okay, so this is my probability of success. Now we need to find binomial gist. A number of successes is 0, number of trials is 20, probability of success 0.15, cumulative false. Okay, so 4%. Probability of that, probability that x is equal to 0 is then 4%. Okay. All right, guys, any questions so far? Is this clear how I got, let's say, from how I expressed that probability as the following conditional one? Guys?
Yes.
Yes.
Yeah, okay, right. So if it's not clear, there are 2 events that partition our, well, there are 3 events, but if we don't look at this event here right now, let me erase that for a second. Then there are right now 2 events that partition my sample space: surviving 0 to surviving in 0 to 4. So this whole region is surviving 0 to 4. And second event that partition my sample space is dying in 0 to 4. Then if I need to find probability of that event, I can work with intersection of this event with so this is probability of dying in 4 to 8. Then I can find I can compose it as intersection of this event with the following 2 partitions. So die in 4 to 8, so dying in second time interval, intersection with surviving in 0 to 4. So this is exactly, this thing here is exactly the probability that I have written down here, plus intersection with the second part of partition, which is dying in first. So this is 4 to 8 intersection with dying in first time interval in 0 to 4. Okay, look, what's the probability of their intersection? Though we said that those two events are mutually exclusive, right? So this is this is 0. So by this reason, we wrote this down as this conditional probability here. Okay. All right, next question. What is the probability that one rat will die in the 8-hour period? So one rat, this is the same. Number of successes is 1, number of trials 20, probability of that, cumulative false, so 15%. So this probability here is 15%. Okay. All right. Next question. What's the probability that 2 rats will die in the 8-hour period? %. Okay. So this is 24%. Can you write a general formula for the probability that X rats will die in the 8-hour period? Evaluate this formula for X is equal to 0 to 10. All right, so this is binomial random variable. So probability X is equal to K, then 20, choose K. Probability of success was, what was our probability of success? Get back to it. 15%, right? So probability of success was 15%, multiplied by 0.15 to the power of K, multiplied by 0.85 to the power of 20 minus K. And then if we substitute those values for K, then we can evaluate these probabilities, okay? So this is simply binomial distribution. All right, any questions, guys? All right, so next problem on CDF. So we have random variable, CDF is given here. We need to find probability that random variable y is less or equal than 2. So how do I find that using my CDF here? So what's the probability of random variable less or equal than 2 or less than 2? This is continuous random variable. So this inequality being strict or non-strict doesn't matter. So how do I find that probability? So when y lies in interval from 1 to 2.7, I should use this formula here, right? So 2 is exactly this value. So this is equal to ln of 2. Now, how do I find this probability here, guys? Don't be shy. So this is CDF, or also known as distribution. We could also give a notation like random variable y has distribution, and that's in here. In case when this small f here, this is PDF. So this is PDF, also known as density. Okay. All right. So how do I find this value, guys? Don't be shy.
ln 2.5 minus ln 2.
Yes, absolutely right. So this is ln 2.5. We still didn't pass this point of 2.7 minus ln of 2. Okay, now again, we said that this being strict or non-strict doesn't matter. So this is same as 2.5 minus 2 as previous one. Now, well, I believe we didn't mention that before, but to find PDF from CDF, we have to simply take derivative of our random variable. So in this case, PDF will be given as 1 over y, okay? So PDF will be given as 1 over y. Okay. All right. Now next, I believe, guys, I won't ask you questions to take derivatives or find integrals, since in our book we are not working with that. But remember, if you want to find PDF from CDF, you have to take derivative. If you want to find CDF from PDF, you have to integrate PDF, okay? All right, now next question is, suppose X is binomial random variable with parameters N and P, shows that expected value of X is equal to NP. So there is an easy approach to find this expected value here. We can denote binomial random variable as consisting of a bunch of independent coin tosses. So as random variables that denotes a single coin toss, let's call it, let's say y, is known as Bernoulli random variable, and it takes value of 1 with probability of p and and it takes value of 0 with probability of 1 minus p, okay? So this is Bernoulli random variable. Y is Bernoulli random variable with parameter p, where p denotes probability of success. Then our random variable X can be decomposed into n independent Bernoulli random trials. So let's say we have y1, y2, and so on, yn. So these are independent coin tosses. So they will take value of 0 if, let's say, coin lands on tails, value of 1 if coin lands on heads, and so on. Then random variable X is going to calculate the sum of these yi's. What kind of random variable X is then? If I denoted it as a sum of those yi's.
Continuous?
No, I mean, what's the name of that random variable? And it won't be continuous, right? Since these are discrete, and the sum of discrete will also give you something discrete, right? So this is binomial random variable, right? So if you toss your coin n times, and then you calculate the number of successes, number of heads on your n tosses, and you calculate the total number of heads on these tosses, that will be binomial random variable. So consider this as like a list of zeros and ones. Let's say n is equal to 4. And then if you sum ones here, you will get 3. So you got 3 heads on your 4 tosses. X, which is represented as the sum of yi's, is exactly a binomial random variable. Now we need to find expected value of X. If I replace expected value with sum of yi's, now we know that expected value is a linear operator. I can switch the sigma sign with expected value. Now we need to find, all we have to do is we need to find, so this is I from 1 to n. All we need to do is we need to find expected value of Bernoulli random variable. So expected value of Bernoulli random variable is then equal to 1 multiplied by p plus 0 multiplied by 1 minus p. So it is equal to p. So expected value of Bernoulli random variable is equal to p. Then I have sum from 1 to n of p's, which is equal to np. So this is how we derive expected value of binomial random variable. Okay. All right. Next problem. We have a couple of minutes. Let's quickly solve the last problem, guys. Or do you have any questions? If you can, we can stop here. I will continue solving this worksheet on Wednesday then. All right, let's quickly solve this problem here. Let x be a random variable with mean mu and variance sigma. Random variable with mean mu and variance sigma. What is the variance of x over sigma plus 10 mu? Variance of x over sigma plus 10 mu. Okay. So then here we factor out 1 over sigma squared multiplied by variance of x. We think of 10 mu as a constant, so it will vanish. Then we have variance of x was sigma squared, right? Yes, sigma squared. So this is equal to 1 then. And all right, guys, let's leave that problem for Wednesday then. Okay, guys, any questions? If no questions, that will be it for today. See you on Wednesday, and don't forget, this Friday we have our midterm. Thanks for watching, guys.
Thank you. Bye.
Bye. Bye.
Goodbye.
Goodbye.